Hello, is this on? Yeah.
Okay, everybody's very quiet. I guess you're ready for the lunch talks. Okay, so I'm here in place of Avi. I hope everybody will behave. I don't want Avi popping up suddenly and saying, you're doing it all wrong. So, as usual, we have 4 talks today. We will start with Enrique Paillas. We'll talk about constraining cosmology with density split clustering. Then we'll hear from Prabhu, new physics in high energy astrophysical plasmas. Then our own Jake Bennett on the Arkenstone wind model, or how we hopefully stop blowing up galaxies and learn to love preventative feedback. No idea what that is, but and then we finish off with another of our locals, Alice Booth, will talk about molecular complexity and the epoch of planet formation. And before we start, I will make a shout out for the ITC discussion. As you know, every week, Thursday, from 11 to 12, we have this discussion on different topics. It's quite amazing, really everybody should be attending. Don't think of only coming to your own topics. It's just so informative. And today it was Daniel Eisenstein who led the discussion on high redshift galaxies. We had other discussions on a variety of topics. I would really encourage everyone to attend that every week. Okay, Enrique.
Okay, thank you very much. I'm Enrique Paillas. I did my PhD in Chile. I'm now at the University of Waterloo doing a postdoc working with Percival. So thanks a lot for the invitation. It's my first time at Harvard, so really happy to be here. I just want to show you some highlights of the work we've been doing during the past year with this very nice group of collaborators, most of them working on the dark energy spectroscopic instrument collaboration. So usually I start my talks saying that really is very exciting times to do cosmology. So our cosmological paradigm rests on this very powerful lambda CDM framework, which, even though being a relatively simple model, it can account for a wide variety of observables, such as the CMB or the large scale distribution of galaxies. There are only a few small details we still need to understand about lambda CDM. Namely, what is the lambda or what is the CDM, or in other words, what's 90% of the universe made of. But we are almost getting there. Please don't cut the funding, we are eventually going to make it. So from the model side, it's very exciting, and from the data side, it's even more exciting. So we have all these multi-million-dollar experiments giving us awesome data to work with. So it's also very exciting and challenging from that point of view, because as we get better and better data, the models also need to be even more accurate. So that's also very cool. For my research, I mostly do what we call galaxy clustering. So I study the macroscopic properties of the universe by looking at the way in which galaxies cluster in space and time. The main approach to galaxy clustering, or the standard approach, is through the so-called two-point clustering statistics, the power spectrum or the two-point correlation function. So this is just a measure of the excess probability of finding galaxy pairs separated by a given scale over a random distribution. And so nowadays people say that we have entered the so-called era of precision cosmology. So this has become a precision science. And this might sound like a cringy statement, but it's actually, it reflects the fact that nowadays we can actually extract information from these two-point clustering statistics very accurately, very precisely. So from the baryon acoustic oscillations on the galaxy power spectrum, we can place precise constraint on the expansion history of the universe. And besides just the baryon acoustic oscillation feature, the full shape of the galaxy correlation function of the Pulse spectrum has a lot of information in regards to the growth rate of structure, primordial physics such as inflation, the nature of neutrinos, and so on. However, even though we have a very good understanding of how to model this galaxy clustering on very large scales, modeling the small scale clustering is actually quite challenging. So our analytic models that are based on perturbation theory usually tend to break down around the scale of 20 megaparsecs to Rayford. So below this scale is actually very tricky to model this analytically. So most of the time this portion of the data is actually just discarded from the standard cluster analysis. But the thing is there are a very large number of perturbation modes on these very small scales. So simply throwing away the data is throwing like almost half of the information, right? So nowadays there has been an advent of simulation-based models of galaxy clustering, which the basic idea is these usually come in the form of machine learning algorithms that make use of n-body simulations for which we can calculate the clustering very accurately down to very small scales. We can only compute these n-body simulations just for a bunch of different model parameters because these are expensive simulations to run. So these machine learning techniques, Gaussian processors or neural networks try to interpolate in this high-dimensional parameter space such that we can get accurate clustering predictions in those regions where we don't have n-body simulations, right? In our work, we have been building accurate clustering emulators that can be applied to current observational data sets, for the moment BOSS and the density survey. So our starting point is the suite of body simulations, this Abacus Summit simulations that people I'm sure have heard of here because Harvard is one of the leaders in the development of this suite of simulations. So these are high accuracy, high resolution n-body simulations that span different cosmologies. So we can take the dark matter halos from those simulations, populate those dark matter halos with galaxies using different prescriptions. In our case, we use a halo population distribution model to populate those halos with galaxies. And then we can compute our summary statistic on this suite of simulations such that we can train neural networks that can learn about how these different observables respond to changes in cosmology or changes in the halo, galaxy halo connection model. So this is an example where we applied this simulation-based model to a simulation that is different to the ones we use for training. Here the dots are the measurement from the simulations, and the solid line is a model we have trained with this neural network. So you can see that we can fit the clustering down to very small scales, but not only the video peak, but also all the non-linear parts below 20 megaparsecs storage. So in theory, this is working well, but we can also apply this to real data. So these are constraints from the SDSS BOSS CMAS galaxy sample, and we have been able to place very competitive constraints on the base lambda linear parameters using these emulation techniques. So the pink contour here are showing the constraint we get from the two-point correlation function, fitting this emulator model to the BOSS clustering data. And in comparison, we are also showing the blank 2018 contour on top of that. Just to see, like, in terms of how does it compare in terms of constraining power with respect to the CMB constraint. So the 2-point is very good, but it's not the end of the story. So essentially, the power spectrum or the correlation functions are measures of the variance of the density field at different scales. And the variance is able to fully describe a distribution if the distribution is Gaussian. You know the mean and you know the variance, and you can fully describe this. So in the very early universe, the roughly Gaussian initial conditions were still largely preserved. So the power spectrum on that stage still is a very fair description of the density field. But at very small scales, in the late-time universe, the distribution of density fluctuations is actually very non-Gaussian. So the power spectrum now is an incomplete description of the density field, and you need to look at higher order correlations in order to capture all the information. So developing techniques that can access this higher order information is an active field of research in cosmology. So we want these techniques to be interpretable and efficient, and at the same time access information that the power spectrum does not readily capture. In our work a few years ago, we proposed this new density split method, And the basic idea is that instead of computing the two-point clustering as we normally do with the power spectrum or two-point correlation function, we first split a collection of random query points in different bins according to what is the local galaxy density around those random points. So you effectively isolate different regions of the cosmic web, low density environments, high density environments, and all the stuff in between, and you compute the clustering for each of these regions independently. And the advantage of this is that this naturally proves the non-Gaussianity of the density distribution. So this is able to access information that leads to higher orders, so it goes beyond the power spectrum, but only at the cost of a marginal increase in computational time. And then you can do the exercise of rerunning the clustering analysis, including this density split information. So this is the same fit to SDSS boss, but now you can compare the pink contour, which is the full information with the density split clustering included, against the green one, which is just the power spectrum or correlation function by itself. You can see that we can significantly increase the constraining power for the lambda CDM parameters. We can get 50% smaller error bars using the very same set of observations, essentially. You can directly constrain those lambda CDM constraints into constraints for F sigma 8, which is the combination of parameters that RSD analysis are mostly sensitive to. So our new constraint is the one shown by the red square over there. You can see that we are finding good consistency with many other studies clustering in the literature, but at the same time we are also consistent at the 1 sigma level with respect to the Planck 2018 lambda CDM prediction. In particular, we are finding that compared to the standard BOSS clustering analysis that only use the power spectrum, we are able to shrink the error bars by roughly a factor of 2, using only a fraction of the SDSS dataset, by including all this additional information beyond the power spectrum. Without the need of additional observations, you can shrink the size of the error bars quite significantly. And you can also take the exercise of bearing the dark energy equation of states, for instance, and then compare what is the constraining power from this new clustering technique compared to the combination of Planck with BEO plus supernovae, which is shown in gray here. So you can see that Planck by itself doesn't constrain dark energy very well, but when you combine it with late time probes of expansion, it becomes very powerful, as shown by the gray contour here. But density split plus the two-point correlation function just by itself, due to the fact that we are already including all the baryon acoustical information, is already giving constraints that are comparable to what is achieved by Planck plus GEO plus supernovae. I'm stop here. I'll take questions.
Perfect timing. Thank you. Okay, we have time for questions. Let me start off with one question. This density split approach that you described, what do you do about galaxy bias? The bias factor, would you think will be different for the two densities?
Yes, good point. So essentially all of the part that regards the connection between the underlying dark matter distribution, or in other words, between the halos and the galaxies, is accounted for by the galaxy halo connection model. That in particular here we adopt this HOD framework in which we statistically populate those halos with galaxies by using a bunch of free parameters that essentially tell you how many galaxies we should put in each halo according to what's the halo mass, right? So this way we can modulate the connection between the dark matter halos and the galaxies. And on top of that, the halos themselves are also biased appraisals of the underlying density field, right? So these HOD parameters are also, in a way, degenerate with these bias parameters that you could otherwise otherwise parameterize this with a bias parameter instead of HOD parameters as well, right? But as you change the HOD parameters, you also change the bias of your galaxy catalog, and that also plays a role in comparing the clustering predictions of your model against the data, right? It's going to modulate the amplitude of the clustering as well.
Yeah, but there are no adjustable parameters here.
So the HOD model itself has something like 9 free parameters. So all of these parameters are varied independently. And these parameters are telling you like how many galaxies we should, how many centrals we should put in each halo, how many satellites, what's the profile of those central satellite galaxies around the halo, and so on. And these are all like affecting this, the amplitude of the clustering, and these are all being varied freely.
Yeah, so
How much better will this be in 10 years when we have the LSST solution?
That's an excellent point. I think the biggest advantage for LSST with this method will be calculating the lensing signal around this density split region. So not only including the clustering information, so you could envision computing the 3D clustering from a spectroscopic survey and then cross-correlating those regions with the lensing maps built from LSST. That's something we are working on at the moment. So this is, we want to extend this to what people know that's called this 3x2 PT analysis, when you not only combine the clustering but also the lensing signal around these galaxies, or in this case, this density split region. We are hoping that this adding the lensing information will be able to break some parameter degeneracies that at the moment are intrinsic to the clustering measurement, right? So you can break the degeneracy between the bias and sigma I, for instance, by adding this extra information. So my answer would be it's going to be promising, but we don't have an exact number yet, but we might have one in a few months from now.
okay. No other questions? Let's thank Enrique again. Next we hear from Prabhu from Princeton.
While I'm getting set up here, I like to make these talks a little bit interactive, so if you're interested in participating in a poll about what you think dark matter is, feel free to scan this QR code. Can people hear me okay?
Yeah.
Okay, great. So yeah, my name is Prabhu, and I'm a postdoc at the Princeton Center for Theoretical Science. And I have this kind of vague title, which is New Physics and High Energy Astrophysical Plasmas. And this is intentionally vague for a couple of reasons. The first is what I just mentioned is this poll. I don't want to bias you by telling you too early what my favorite dark matter candidate is, but I will after this slide. But the next point that I wanted to make is that some of the ideas that I'll talk about here are broadly generalizable to various dark matter candidates for new physics, as well as various astrophysical settings. But in the interest of scope and time, I will focus on my favorite candidate and my favorite site of high-energy astrophysical plasmas, which are the magnetized regions surrounding neutron stars. And so for those who want a few extra seconds to vote, you have just that before I tell you what my favorite candidate is, which are axions. And axions are broadly defined as ultralight bosons with the extra property that they're odd under mirror reversal or parity symmetry. And these particles are predicted very generically in extensions to the standard model of particle physics, for example, string theory. They were also proposed in the late 1970s to explain the seemingly unnatural smallness of the neutron's electric dipole moment. But I'm going to kind of gloss over a lot of the particle physics details and just talk a little bit about some of the phenomenology and how we go about looking for axions. So one generic prediction is that axions are expected to couple to electromagnetism through this operator, where G here is some very small coupling constant, A is the axion field, and E dot T are your electric and magnetic fields. And this coupling can be exploited in a number of ways. So first, if I'm able to generate a region either in the lab or in an astrophysical setting where I have an unscreened E dot B, such a region can actually produce axions. And you can kind of see that in stellar processes. So a question I often get when I talk to astrophysics audiences is, okay, you're talking about a very weakly coupled particle. How could this possibly have any effect, order 1 observable effect on an astrophysical system? And one of the good answer to this question comes from a similar particle, which is a neutrino. So as we know, neutrinos are important for cooling in a lot of astrophysical systems, such as supernovae. And similar processes can occur, for example, in stars. So the E dot B that I generate in a star comes from what's called the Primakov effect, where I have some electric field, say coming from some ion, and then some thermal photon. And when this photon hits the electric field, you can produce an axion. And because axions are so weakly coupled, like neutrinos, they can just escape from the star without any issue. And you can contrast that to photons, which have small mean free paths in the star. So they kind of bounce around and random walk their way to the surface, and then they're emitted from the surface. Whereas something like an axion or a neutrino is emitted throughout the entire volume. And so this will place pretty strong constraints on the axion by saying that, if the axion is sufficiently strongly coupled, then I can actually mess with the evolution of stars. And this will, these kind of stellar evolution or anomalous cooling constraints are shown in green here. And just the way to read these kinds of plots, this is the strength of the coupling, and here is the axion mass, and any shaded region here is ruled out. Another thing you can do is what we call indirect detection, and that is to say if I have some axions, in another property of this coupling is that in the presence of some static field, axions can actually convert into photons, which may be detectable. And this magnetic field, which I show here, can either be a stellar magnetic field, it can be the magnetic field of the interstellar medium, or even a magnetic field that we generate in the lab. And here are some of the shaded constraints that you get from these kind of indirect searches for these kinds of photons in various astrophysical systems. And I want to focus in particular on some of my work on looking at pulsars as factories and sources for axions. And this maybe shouldn't come as a surprise because, as many people may know, pulsars or neutron stars more generally have some of the strongest electric and magnetic fields in the known universe. And so I'm going to dig into some of the details of this. But first I want to motivate pulsars as laboratories for new physics. And this is not a new idea at all. People have been looking at pulsars as laboratories for new physics for decades now. For example, so pulsars here are rapidly rotating neutron stars that emit these beams of radiation. And the timing of these pulsars is so precise that they're kind of very good astrophysical clocks, as has been exploited in pulsar timing searches for low-frequency gravitational waves. But also, as I mentioned, pulsars are very good particle accelerators. So they're just giant astrophysical accelerators. And we can kind of see that by looking at, for example, the spectrum of the Crab pulsar. You see this kind of thermal-looking feature that peaks in the X-ray. But then there's considerable non-thermal emission at higher and lower energies in both the gamma ray and the radio band. And this is kind of indicative of some kind of unscreened electric field leading to particle acceleration. Unscreened electric field here means a large E dot B. And if you've been paying attention, you remember that E dot B is exactly the term that couples to axions. And so, as I'll show, it is the case that pulsars are actually very efficient axion factories. And I'm not going to go too much into the detail about how pulsars work. There's been a lot of research over the last few decades in trying to understand even normal electromagnetic emission from pulsars, and specifically this radio emission. And some of the recent results from particle and cell simulations performed by a number of my colleagues that I list here, they have a model in which near the surface of the neutron star in what's called the polar cap region, these are regions right above the neutron star surface and near the magnetic pole, you have exactly one of these unscreened gaps where there is a large E dot B. But of course, as we all know, that vacuum doesn't like large electric fields. These electric fields become unstable to sparking, which is really the production of electron-positron pairs. And so what happens is this electric field kind of gets dynamically screened. And I want to particularly draw your attention to a result from these simulations. This fourth panel is plotting exactly the spatio-temporal evolution of this E dot B. And the result of these simulations is that this dynamical screening leads to the production of plasma waves called Langmuir ordinary modes, which are thought to be the progenitors of the radio emission that we observe. And it just so happens, as I pointed out in a couple of years ago, that this same physics may be responsible for axion emission. And if axions are emitted, their phenomenology looks totally different than that of the radio beam. So for example, the radio beam is collimated, whereas axions are emitted kind of quasi-isotropically, and they lead to considerable off-beam radio emission. And this is heavily constrained by pulsar observations. You know, we see the pulses, but off-beam, there are quite stringent flux limits on this flux of this radio emission. And this allows us to set some very loose constraints on axions just by saying we don't want to overproduce radio flux by having these axions leave and then convert into radio emission. And so this is an analysis that we did for 27 somewhat admittedly randomly selected pulsars. And the constraint that we get is kind of the strongest over a range of masses. But as I mentioned, there is considerable prospects for making these bounds better. So for one of the things that I mentioned is that I look at only kind of low field pulsars. And this is due to large modeling uncertainties as we go to high magnetic fields. And we expect that the higher the magnetic fields, the better the constraints. And this motivates this exotic class of objects called magnetars. And part of my interest is in trying to understand magnetars at purely the astrophysical level. And this is kind of a requirement before we can ever hope to apply them to anything like an axion. And so this is kind of the summary of some of the things that I think about. And here are some related either follow-up or ongoing works related to axion emission from pulsars and how we might use this kind of story to help our understanding of both axions and pulsars. And so with that, I'll stop and take any questions.
Thank you, Ani. Okay, you have a clock on your computer?
No, I
Just when it was time, okay. Okay, so, yeah, please.
Is the kind of energy or mass range, I guess, that you're covering at that point, is it still, are there places where there are better candidates, axions better candidates to be dark matter than others? And kind of, where does that lie?
This is a strongly observer-dependent question, but I think what people say, so one thing that I didn't mention is that this story does, so a lot of these constraints I haven't actually shown, they rely on the assumption that axions make up all of dark matter, which is not, it's a difficult thing to achieve, but people generally say that the 10 to the minus 7 to 10 to the minus 4 range is where it's easy to produce 100% of dark matter with axions. Now, of course, this doesn't require that, but again, different people have different preferences. Of course, small-scale structure people, maybe 5-ish years ago, said that you go all the way down to maybe 10 to the minus 22 EV, and goes, because this can resolve some small-scale structure issues and give you the right dark matter abundance. And I should mention that this, you can't really see it in here, but this should extend all the way down to low masses. It probes anything, any axion mass less than maybe 10 to the minus 5 EV. But yes, it's a good question, and it depends on who you ask, but I would say roughly in this range here.
So I missed one detail in your talk. Looking at pulsars, and you're looking for off-pulse emission from this process.
Right.
What exactly do you do? Do you look at the radio pulse profile and look for a tail? Is that what you do?
So we just look at, yeah, so basically we just set our constraint by looking at there are flux, so they usually have pulsed flux limits and unpulsed flux limits, which are taken by just the kind of quiescent, non-off-beam radio emission. And I've kind of glossed over some details, but when we produce axions, we do some ray tracing analysis to see what does the kind of angular distribution of the outgoing radio flux do just to axions look like. And then we compare this with the full pulse. Of course, this includes comparing it to the on pulse, but you don't get much of a strong constraint there because you're dominated by the regular radio beam. So it is actually kind of a full analysis over the whole pulse phase, but the dominant constraint is coming from the part where the beams are facing away from our line of sight.
Right, okay, yeah, that's good. So does it have to be only pulsars? Any non-thermal source of radiation must be doing this, I presume?
Exactly, yeah, so black holes would be another good candidate for this. And one of the things that I didn't talk about is that some of the axions you produce are at velocities less than the escape velocity of the neutron star. And so this allows you, this is quite a generic prediction that if axions exist, making no statement about their relationship to dark matter, you should get these very dense clouds of axions around neutron stars. Now for black holes, if I'm producing something anywhere near the horizon, the fraction of the phase space that's emitted into these bound orbits is enormous. And so you might expect processes like this to occur for black holes as well, and even with these very dense clouds have some interesting phenomenology. Since they couple to photons, it might lead to, say, spectral distortions to certain emission and things like this. But this is something that we haven't really looked at.
So related to the first question of Ramesh, then I stop. For how long, related to the dot terms, for how long do you need the electric field barrel to be coherent or over which scale in order to have a good production of axons?
So it's somewhat agnostic. It's kind of whatever, as long as my axion, it's not kinematically forbidden, whatever the length and time scales of these fluctuations are, this will set the fluctuations of the axion spectrum. And I should clarify that this is not a single process. It's not like one time there's a screening and then it just stops. This is kind of a cyclic process that's happening over and over. As you screen the electric field, the gap opens back up, it's re-screened, and so it really is approximately, not periodic, but certainly cyclic. And so the answer to your question depends on what the axion mass is. If it's in the range of, what I mentioned, 10 to the minus 8 to 10 to the minus 5 eV or lighter, then you're just producing the axions at the spectrum of whatever these fluctuations are.
Very good. Thank you, Ani. So now Jake will explain the title of his talk.
Yeah. Can you hear me all right? Okay. So, yes, I'm going to be talking today a bit about what I've been up to most recently as part of the Learning the Universe collaboration, which doesn't have a logo, so it's just random. Want to thank my collaborators, Matthew, Drummond, and Greg, particularly Drummond in this case, given I got asked to do this talk at kind of the last minute, and I've stolen some slides from him. So Arkenstone is a wind model. We're talking galactic winds here, not solar winds. And there are various wind models in the literature that try and do various things. You use them for stellar feedback to try and regulate how stars form in galaxies, etc. over time. But there are various things that don't work. So this is vaguely what I'm going to run through in this talk, is why we need another one, what is Arkenstone, what have we done so far, and what do we intend to do with it. So, first point, this is one of Drummond's slides, they're very pretty. So we have the nice cosmic web, as we've already kind of seen a bit earlier, and you zoom into one particular region on megaparsec scales, you get a galaxy. This is a gas projection and the different phases of gas, and there's all sorts of stuff knocking around. But how that interact, you have inflows coming from the cosmic web onto this galaxy, and the galaxy is doing things and blowing stuff out. But the cold gas is harder to look at. If you zoom in on these regions, you find still this cold and hot interaction on smaller scales. Kind of kiloparsec scales, you're looking at the interstellar medium. If you zoom in even further, on the edges of some of these teeny clouds, on parsec scales and potentially even less, you end up with this interaction between cold clouds in a hot medium. Now this kind of comes into a lot of different aspects of things. You can have this in the intracluster medium around galaxy clusters, you can have it in the circumgalactic medium, when you have cold clouds being either being accreted onto the galaxy from the intergalactic medium, or being thrown out from the central galaxy. This kind of interaction between the cold and hot phases is quite an important process, because the cold gas is what you need to form stars, right, fundamentally. And so then how you get from hot to cold to hot, and what amount of gas is in any of these phases is hard to simulate. And that's what I do. I'm a simulator, but doing parsec scale things, when you try to do megaparsec scale galaxy simulations, is not really feasible. You start to struggle quite rapidly. So the idea of Arkenstone is to try and shove all of that stuff into below the resolution limit model, where you kind of model the interactions on this, what we call subgrid scale, and what the results then that you get on kind of larger scale galaxy formation, they are kind of, you see how that affects the larger scales. And that is what exactly we're trying to do. And so the small scale processes are basically the parameters that go into our subgrid model. This kind of scale here is kind of the interaction between these clouds and the surroundings, which we've used the subgrid model for. And what we're interested in is these kind of large scale ramifications of this problem. So this is broadly how these work. So we have a galaxy, and supernovae are going off, doing what they do. We're kind of mostly talking about supernovae here. I'm sure there's other feedback, but we can't resolve that anyway. So, and we know from observations that galactic outflows are multi-phase. You have a hot component, an ionized component, depending on what you want to call it, and you have cold gas as well. So this cold gas is not likely to be volume filling, it is embedded within the hot wind. And we are going to model this using a distribution of clouds, basically, that are embedded within this hot wind. And then what you take here is that each individual cloud that is this subgrid model, you have parameters, you parameterize the exchange of mass and momentum and metals between these cold clouds and the hot wind surrounding it by this turbulent radiative mixing layer model, which is kind of based on really quite high resolution simulations that are much more resolved. But kind of the reason we're doing this top wing here is that and I'll show this in a moment, but in kind of standard cosmological simulations so far, to regulate galaxy formation, you end up with gas falling into your galaxy and you have to throw it back out again. And that is kind of the only way we've been able to figure out how to do this. And you have quite high mass loading factors. And that's what the cold phase is generally expected to do. It carries the mass out. But one thing that we can't resolve very well in existing simulations is the hot phase. And that, while it doesn't have a huge amount of mass in it, has a lot of energy in it. And so you really start changing the way that you're going to regulate the formation of stars in these galaxies. Excuse me. So this here, the three panels here, starting on the left, or the top one's density, bottom are temperature. The starting on the left is a model basically similar to illustrious TNG, the kind of state-of-the-art simulations, where basically we have mass in the center of the galaxy, in the ISM, stars form, you throw that mass out. You have very high energy, mass loadings in this. I believe the mass loadings in TNG are basically, you take the amount of energy you get from your star formation, you times it by 7, and you throw it out. That's kind of, this is one of the tunable parameters that you can change to basically to regulate star formation. And that is not especially physical that you're throwing out this much mass. This middle panel is when you start to turn up the energy loading of these winds, and so you start to blow this hot wind out. But what you find is when you start to put a lot of energy into kind of regions where the resolution is lower in the simulation, you end up with blowing these massive cells that are even bigger than the entire system you're trying to simulate, which is not good. And you end up getting the wrong wind properties from what you'd expect from kind of analytic expectation. And so this is the Arkenstone model on the right, where you have this hot wind being launched, and you are kind of correctly resolving how the hot, high specific energy loaded winds recouple to the galaxy, recouple just outside the galaxy, and you're blowing this hot wind, which is kind of completely absent. This phase of gas is completely absent in this left-hand picture here. And so yeah, this is just kind of illustrating that the middle problem here is that when you put a lot of energy into a cell, you end up with very low densities, and if you try and do this in the circumgalactic medium, you end up with enormous cells bigger than the galaxy themselves, which means you don't end up actually resolving the wind launching very effectively. You just have big blobs occasionally going on. So, a couple of movies now. So this is the full Arkenstone model. So I was just talking about the hot phase there. What we then do with it is we also embed cold clouds in. So you can see here, this is density and temperature again. You have the hot wind doing what it's doing. It's launching at fairly high velocities. And every single particle here is representing a cold cloud of 1,000 solar masses. And it's launching, and they're interacting with the hot wind around them. You might see at some point some of these particles disappear. It's because they've shredded, they've lost mass as they go along. Now, there are different examples you can do with this. So, for example, if you make the mass of those clouds smaller, they shred much more easily. And so they don't really get very far out of the galaxy, and you just kind of lose them all straight away. And do I have the other slide in here? No. But if you go the other way and you make these things larger, they can actually grow by cooling more gas onto them. And you can end up with more cold gas just kind of thrown out there into the circumgalactic medium. And so the CGM will be a kind of key probe of these kind of processes and the amount of cold gas being thrown into the CGM. So these are all isolated galaxies as I showed before. This is a cosmological zoom simulation. So this is a Milky Way mass galaxy at redshift 0. On the left here is the kind of initial, the kind of fiducial model we end up with, where we've got, to regulate star formation, you just have to throw stuff out. And you can kind of see it here, there's a lot of cold material being thrown out, some of it's falling back in, you kind of get these ejective cycles and you're throwing stuff out all the time. With Arkenstone, and this was just the first test, so this was quite fun to see. Oh, I've only got like the 2 slides left. You end up really making this a lot hotter, and you changing the properties of the CGM here, and you're destroying some of this cold gas. So you're kind of starting to regulate star formation in a different way. Funky videos, blah, 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 get the point. And so just this top panel here is the important one here. So for this dotted line here, this kind of faded dotted line is the star formation rate in the left-hand model, the older star model, where you're throwing out lots of mass, and you kind of regulate star formation about 1 ton mass per year by redshift 0. With the Arkenstone model, admittedly with the parameters we still need to kind of figure out exactly which energy loadings to use for these. Well, this doesn't throw mass out at all. This has no cold clouds in it, the ones that examples I just showed. But you can already regulate star formation quite effectively just by blasting this hot wind out of the galaxy and cutting off inflows and outflows. So there's potentially quite a very different way to regulate star formation in galaxies, and it'll hopefully kind of shift the idea of how we do this in simulation down in the real universe going forward. And what we want to do next is nice big cosmological simulations doing this. Can can we reduce the need for like really strong AGN? Can we get a realistic galaxy population without just throwing out crap loads of mass? I don't know. We'll find out. I'll come back in, I don't know, I'll say a year, hopefully, and tell you. So, yeah, that was enough. Thank you very much.
Thank you, Jake. John.
There are some special diagnostics for turbulent mixing layers, like charge transfer X-rays and overionized gas. Does your turbulent model do that?
In terms of the kind of parameterization of the mass fluxes and momentum fluxes and etc. between the thing, I believe they do have some of that in the kind of high resolution simulations that this model is calibrated on. In terms of what we have in this, not yet. So we kind of we're trying to get it to work first, and then the next thing we're going to do is like, right, how do we make kind of mock observations of these cold clouds being in the TPM? And we've got to figure out the best way of doing that, really, because each of these particles that are showing there represents the distribution of clouds. And so how you then make kind of mock observations out of that will be kind of the next step going forward.
So you made this point about the need to resolve the like hot but volume filling, if not mass tracing component. How does that relate to, like, I mean, when I think about the cosmic web, there's a lot of space that isn't full of mass, and that's part of what lets you do these simulations when you refine really aggressively on the mass tracing region. So how does that relate to this goal to kind of look at that?
So what we found is that the hot phase, to get the larger scale properties of the hot wind right, we need to resolve kind of this recoupling of the hot phase on scales just outside the galaxy.
Like a couple
And
scale
so-
heights or something?
Yes, exactly.
Yeah.
And so outside of that, if you degrade resolution, you kind of recover the same properties. You have to get this, like, the launching of this wind right,
I see.
and then the properties further out generally converge. Now, there are differences, of course, when you have resolution higher further out, but that is kind of getting into computational things that we really struggle to do.
Yeah.
But in terms of the kind of the wind launching and driving, that's the scale that we found is the important one that we need to try and resolve, and so that's what we're focused on.
So you showed that the properties of the cold wind depend on what is of the size of the cold, right?
Yeah.
Does the properties of the galaxy depend on it? And if so, how do you choose?
So that is a very good question. We don't know fundamentally what cloud distribution exists in from observations, as far as I'm aware. At least, if someone would like to correct me on that. At least in the, do you know in winds or just in the ISM?
Well, if you look for molecular and atomic material surrounding galaxies, you sometimes see that. But I think it could be argued that this is always the result of galaxy-galaxy collisions and the galaxy being torn up and stuff being ejected into galactic space. But it sometimes happens, but it's rare, and it is observable.
Yeah. Well, yeah. So in terms of the impact on the galaxy, that remains to be seen. There's kind of the isolated galaxies have been kind of the test so far of seeing how, and the balance that we get in the star formation regulation between the hot and the cold phase will, I think, be the really interesting place to push going forward, because no one's been able to look at this hot phase and how it can regulate star formation at all before. And so that's kind of the cool hot thing that we've found, is that you can regulate star formation without throwing any cold gas out at all. And so that's probably slightly overkill with the hot phase, but if we balance it with some ejection of cold gas, I think that will be the kind of the sweet spot that will be quite interesting to look at in the future.
Very good. Thank you, Jay.
Thank you.
Okay, final talk will be by Alice Booth. So let us play fellow.
So what I'm interested really is what molecules are around when planets are forming. So that can be simple molecules and complex molecules, or just being interested in the elemental makeup of the gas in these young planet-forming disks. So protoplanetary disks don't disappear out of nowhere, so they typically form, or they do form through the star formation process. You start with these cold clouds of dust, gas and dust, you form a star, you form a disk, and then you form a planetary system. And we know that these dark clouds, they're full of dust and ice, and we can form complex molecules in them quite easily without kind of much effort. When you go to young protostars, we see a lot of complex molecules in the gas that have been sublimated from these ices. And what I'm interested in is what's going on in the next stage in these kind of planet-forming disks. So what is the complex content of these objects, and how does this feed into what we know about planetary systems and comets? So we've detected about 30 different molecules in protoplanetary disks so far. This is a pretty big number, I think, for disks if we think of all these different molecules, but when you look at other regions in space, it's pretty few. So these are colored by basically the elements, so the blue ones have oxygen, the green are just carbon and hydrogen, you have nitrogen with the purple, and then orange with the sulfur. So we've got a whole host of different elements. And everything in bold, I would say, has been detected at sub-millimeter wavelengths. And most of that is really done now by interferometers. So the ALMA is kind of becoming is the powerhouse of this field, right? All of these large 6, 7 atom molecules are only really detectable with ALMA. So ALMA is the Atacama Large Submillimeter Array. This is a giant observing facility in Chile. This is a picture of ALMA in the snow. People don't realize it snows up there, and I think it's pretty neat. So to kind of set the stage with ALMA, what we can do is look at young planetary systems on, you can do better than this, but typically about 10 AU scales at a distance of 200 parsecs. So we can start to resolve, really almost solar system scales. The sensitivity, if you care about Janskis, per kilometer per second, if you're looking at lines, you can get less than 1 millijansky, so that's pretty great. And the frequency coverage of ALMA is pretty vast, from tens of gigahertz up to almost 1,000. When we look at the dust in disks and ALMA, this is what we see. This is a picture of TW Hydra, our nearest protoplanetary disk with ALMA. So this is what we call continuum emission. It's the thermal emission from the small dust grains. And what you can see there are lots of ring structures. So the popular kind of explanation for this is you might have little planets sitting in between these gaps that are carving out orbits and so forth. And if you zoom in right to the center, we can even see structures on 1 AU scales. So ALMA is really powerful when we're trying to look at the dust and figure out how we can form solar systems. And what about the gas? So disks have a range of temperatures and densities, and that means we can have different regions where we can have molecules in the gas or the ice. So if we start from the star and go radially outwards, it gets colder. So in the inner few AU of your disk, you're going to have a lot of water, and also a lot of complex organics, because these kind of come off the dust grains at a similar temperature as water, 100, 150 Kelvin. As you go further out, the region that we can probe with ALMA on tens of AU scales, we typically see cooler carbon-rich gas. So cool about 20 to 50 Kelvin, and hot, I would say, is over 100 Kelvin, just so we see what I'm talking about here. So this is nice, but when we look at disks, they're not actually smooth. They have a lot of structures. So this is a gallery of acid disks that are called transition disks. So this is kind of just a terminology where they have these large gaps, tens of AU almost, that we see here. And you see these are all different kind of side scales, we have different asymmetries, you have multiple rings. So disks have a variety of structures. And if I pick out one of our favorite disks, this is PDF-70. This is a disk where there's evidence for young giant planets within this gap. So it's pretty plausible to suggest that a lot of these structures are caused by giant planets or slightly higher mass planets. So disk structure then might also affect the disk chemistry. So this is our cartoon again, but I've cut a big hole in the middle of this. So we have a large gap, maybe because we have a forming planet, and we have our ice reservoir sitting out at tens of AU. It might be that this material, which is typically shielded by the rest of the disk, is now exposed to more heating and UV radiation from the star. And therefore we might expect to maybe detect some water or comets on tens of AU scales in objects that we typically didn't think that we could. So I'm going to talk about this disk today. This is a nearby disk, IRS-48. It's an Ophiuchus. It's a young A0 star, about 4 or 5 million years old. It's about 135 parsecs away. So on the left, what you see is the CO gas in the disk. So this is tracing the bulk H2 gas in the object. So we have a central hole, and we have this ring of gas. And we call this a dust grain. There'll be these structures. So these large grains are basically decoupled from the motions of the gas of the disk. And the kind of explanation for this is probably due to some sort of hydrodynamical instability caused by planet or companion orbiting. But that doesn't really matter too much. Because what I care about is the chemistry. And so we have methanol in this disk. And methanol is our simplest complex organic. So what you see here is the methanol emission. This bright blob is sitting where this bright blob sits doing. So what we've kind of got here is this complex gas reservoir is linked to the large dust, which is probably where the ices are hosted. Slightly sitting just kind of on inside of the dust as well. So methanol is pretty important. I think we call it the simplest complex organic molecule. So methanol we can only form efficiently in the ice, so we can't make it in the gas phase. So if we see methanol in the gas, it has to come from the ice. We can't synthesize it in the gas. And the most efficient way to form methanol is on CO ice-coated dust grains. So you have your dust grain, you have a layer of CO, carbon monoxide ice, and you successively just add hydrogens. You keep adding hydrogens, you get to formaldehyde, eventually you get to methanol. And that's kind of the way we synthesize methanol. But what's great about methanol is that it kind of is the backbone for a lot of complex organic chemistry on the ices. So if you have your methanol, you have more hydrogens, more carbon, oxygen, or something B, you can make a whole host of complex organics. Molecules like methyl ether, methylformate, acetaldehyde, and a lot of cool stuff. So if we have methanol in the gas, it has to come from the ice, and that's telling us this ice reservoir is potentially rich in a lot of other complex organics, which is pretty good when we're trying to think about building up to almost larger prebiotic molecules. So this is what we got. We got our disk, we found the methanol that I suggested that we would see, but what's interesting is that this disk is quite warm. So the dust in this disk is kind of warmer than about 20, 30 Kelvin, and that means we can't have CO ice in the disk, right? So the way to get the methanol in is we have to start with methanol when we form our disk. So during that turbulent, crazy process of star formation, the ices, some of them must remain intact and kind of inherit into the disk material itself. This is nice evidence that these disks are inheriting material from earlier stages of evolution from dark clouds. We actually detect a lot more complexity as well. We find bigger molecules. So we've got methanol on the left. I've got the names and the chemical formulas. So we got methylformate, CH3OCHO, dimethyl ether, which is a little similar but different, and ethylene oxide as well. And these little blobs are all sitting in the same place, so we think they're all kind of coming from the same process, this ice sublimation. And what's really cool is ethylene oxide is actually a cyclic molecule, so it's ringed. Basically, you have 2 carbons and an oxygen. This is the first time we found such a heterocyclic molecule in a disk, so that's really cool. And this is interesting because these molecules have other names, so this is also called epoxide, and this is a 3-member ring, but once you jump to a 5-member ring, you get to fluoride, and that almost forms the backbone for something like ribose. So disks, we think, probably have a lot of complex chemistry going on, and we might not be able to see it, but we can see the smaller molecules that can tell us about what could be happening. And we actually found a lot more complexity than we expected to see. So on the left, you have a plot of how abundant these 2 molecules, dimethyl ether and methylformate, are with respect to methanol. This is a percentage, so if you look at these young class 0, class 1 protostars, these molecules are detected at about the 2 to 3% level with respect to methanol. So they're not that abundant. When we jump to this disk, what we're seeing is that they're at a 20-30% level. So we have about 10 times increase in complexity when we're going to this other system. And then when we look at this ring molecule that we have, ethylene oxide, it has an isomer which is not ringed, acetaldehyde, this one here. And typically this one is about 10 times more abundant, but we don't see it at all. The ratio is about 1 is a rougher limit, right? So we have a lot more of this ring molecule than we expected. So this might be some evidence that what's happened, as these ices are sitting at the disk, they might be being processed. We come back, interior ices, they're going to sit in the disk for at least 1 million years. There's a lot of stuff going on. We could be enhancing our ice reservoir, right? We have the UV from the star hitting these ices. It's not in a region where they're hot enough to sublimate. You can basically break apart molecules, you create little radicals, say breaking apart your methanol into little pieces, and they can recombine and they can form more things. And disks are typically quite dense as well, so you have a lot of space really to form more molecules. We actually now have 3 disks where we see the same ice sublimation signature. the one we talked about in the middle, and the two on the left. So this is showing that this is typical, and it's not just this one disk. And we have some data coming to look at 6 more systems to find more complex molecules, which hopefully will be very nice. So to take away, I'll thank my collaborators and the students at Leiden Observatory that I worked with when I was there. So we know that planets are forming in these chemically rich environments. We can trace things on tens of AU scales of ALMA, which is great. This sublimation of ices in these disks is letting us see what typically we can't see that's hidden in those disks. And we think that these ices get inherited from the earlier stages of star formation. But there seems like during the lifetime of the disks, we might have some processing of these ices, and that may actually enhance the organic reservoir that we have available to form comets and icy moons and things like that. Alright, so thank you for listening.
So with the enhancement of the molecular intensity with UV exposure, is that specifically enabled by their UV large gaps from the planets, or is that a generic analysis?
I would say it's probably generic. I think the fact that these disks have the gaps changes the thermal structure so that we can see them in the gas, but they're probably in the gas.
I don't know the free spectral range of your typical ALMA observations, but I'm just curious, just a general question. Are there transitions that are unidentified? Do you see evidence for additional molecules that no one's identified, or no, is everything neat and tidy?
Typically we can figure it out. Sometimes it gets more complicated if lines are blue or redshifted due to, say, motion in the disk. But normally we can identify those things. Disks are not very line rich. When you go to protostars or AGV stars, you have a lot of unidentified species, but for disks, typically we can figure it out.
Okay, thank you.
Yeah.
A lot of the processing is happening due to UV radiation from the star. In molecular clouds, though, like the predecessors, cosmic rays play a really important role in determining the chemistry. So I'm curious where this transition occurs between, say, in molecular clouds, cosmic rays play an important role in the chemistry, but in the protoplanetary disks, it's not.
Cosmic rays, yeah, well, cosmic rays are also going to be happening in the disk as well. And typically when you get to the very shielded layer of the midplane, they are your only source of ionization. But the disks have quite a vertical extent, and there are layers where you can get into.
Okay, thank you, Rajesh. So I wish you all a good Thanksgiving. We'll meet again in 2 weeks.